What's up, everyone? Today we're going to do a problem where we're going to try and determine whether or not a string is in a dictionary, and if it's not in the dictionary, we're going to determine how many is the minimum number of characters that we need to remove from the string to make it a valid string in the dictionary. So let's look at this example here that I have, and our dictionary is just these three strings A, and AAA. And then our query string is ABC. So as you can see, obviously, ABC is not in our dictionary, but we can find a substring of ABC that is. Or we can find a string that we could get by removing characters from ABC that's in our dictionary, which is this A. And hopefully, obviously, we can remove the B and the C and get A, and that's two deletions. So we have to remove two characters to get a valid string in the dictionary, and so our output is 2. And let's jump right into thinking about this problem. And the first thing that we always want to do is clarify the problem, make sure that we fully understand it, and ask any questions that we might have of our interviewer. So the first thing that I want to do is just clarify what exactly are the parameters of this dictionary that I'm getting passed in. So if it's pretty obvious from the way that the question is phrased here, but a lot of times in an interview it may be less clear than this, because especially since you can have this two-way dialogue with your interviewer, they're going to want to see that you actually are asking questions and trying to actively understand what the problem is. So in this case, because our dictionary is a hash set, that tells us something very important, and that tells us that we're going to have to do a completely blind algorithm to solve this. We don't know what the character or what the strings are in the dictionary, because all that we have is the hashes of these strings. So what we could do is we could go through, we could say like all the strings, we could calculate what are all of the strings of, up to X characters that are in the hash set by basically going through all possible strings, hashing them, and then seeing if they're in the hash set or not. But that would be really inefficient, and that might be a reasonable thing to do if we're going to be calling this repeatedly with the same dictionary, but it's probably not going to be an efficient thing to do in the context of this problem. So for all intents and purposes, we don't know what the words are in the dictionary, and so we can't do anything clever. We can't look at the words in the dictionary and see how they relate to the query string that we have. And so what we have is we're going to be able to say, the only thing we can do is say, is string X in the dictionary, or is string X not in the dictionary, and we can't do anything else. So we want to clarify that with our interviewer and make sure that we understand. I guess pretty obvious from the description, but we also might want to double check whether or not it's an option to potentially add characters in to the string to make a valid string. We should ask whether we're calling this once or repeatedly, because as I mentioned a second ago, it might make, if we get in this dictionary once and then we're going to call this hundreds of thousands of times, it probably does make sense to do some sort of pre-processing, and then we can optimize our search algorithm by knowing what strings are in the dictionary. But it's good to clarify these sorts of things. Another thing we might ask is, what are we going to do in the case that the query string is not in the dictionary? And that's something that, we might want to think about what the answer is. I think in this case, it makes sense to return -1, because our answer set is going to be not the set of non-negative integers. So 0 to infinity, or 0 to max int, right, is going to be the possible answer, the possible responses to a valid query. And therefore, I know that the response can never be negative. So by returning a negative number, I can use that as an error code, basically. So let's think about how we're actually going to solve this problem. And when I look at this problem, the first thing that comes to mind for me is breadth first search. And it may not be super intuitive at first, because it's not really necessarily clear how we would translate this into a graph. But let's look at how we would do this how we would create a graph or a tree for the example query. So we can in this case, we're going to have a tree that it's not going to be a binary tree. We're going to have the number of children is going to be dependent on the number of characters in the string. So we're going to start with 3 children, and the children would be AB, AC, and BC. And then we can create children for this. We're going to have our, let's see, we have, these are all going to be single character strings, but we have A and B, we have A and C, we have B and C. And now what we can do, so we want to find basically we want to find the longest string that we can get from our query by removing individual characters that is in our dictionary. And we can do this by basically searching in order. So what I did here is I constructed a tree where the first level is the original string. The second level is the string with 1 character removed. This level is a string with 2 characters removed, and so on and so forth. If we had a longer string, obviously it would be a deeper tree. And we can go through this in order, and we can just check, is the string in the dictionary or not? So we start here and we can check, is ABC in the dictionary? And no, it's not. So we come down and we look at these, and this is checking all of the possibilities with 1 character removed, and it's not any of these. And then we come down to here and we get A, and A is in the dictionary. And by doing breadth first search, we know that we're always going to, the first string that we find in our search that is in the dictionary is by definition the best result. Because that's the advantage of doing a breadth first search, is that you're basically searching for the best possible result by searching for the best possible. You start with the best possible case and you slowly degenerate until you get to the end. And so you know that you're basically going through all the possibilities in order of what is the best possible option to the worst possible option, and you know that when you get to an option that is possible, that is by definition the best option because you're going through them in order. So if we look at this here, this is basically what I'm going to do. I'm going to do a breadth first search and go through all of the possibilities and check whether they're in the dictionary. But it's worth discussing here briefly that this is not a very efficient algorithm, and I'll talk about the actual time complexity later, but you can probably tell that this is going to grow very, very rapidly because we don't know we can't do anything intelligent when we're searching in the dictionary. We just know that we can search in the dictionary. And so by definition, we're going to have to search for every possible combination of characters that we can get by removing characters from our query string. We're going to have to search for every possible substring to ensure that either we find the answer or we find that there is no possible answer. And we're optimizing this slightly by going through it in order from best to worst. So we know that most of the time we're not going to have to go through all possible combinations because we will find the answer before we go through all of them. So the worst case is when our query string or when there is no substring in the dictionary. But it's not going to be super efficient regardless of what we do. So that's sort of unfortunate, and there's not really much we can do about that. One thing we can do is, you may notice here that we have these strings are repeated. And this would obviously get a lot worse if we had multiple levels, because you would repeat substrings and you would repeat longer substrings, and then those would obviously repeat all of their children. And so we'd like to actually catch this before we end up with all of these substrings, and that will help our algorithm be slightly more efficient. It's not going to actually improve the time complexity in any meaningful way, but what it will do is it's sort of the same as saying that, you could have a coefficient of 1 or you could have a coefficient of 1,000, and both algorithms are O of n, but like one is clearly better than the other. So this is basically what we're going to do here. It's a small optimization, but it will make a little bit of a difference. And we'll do that by checking when we because when we do breadth first search, we're going to create a queue, and we're going to go through the queue as long as there are elements in the queue. and we're going to just check that our element has not been added to the queue before we add it to the queue. And unfortunately, there's not really a good data structure for us to do this with, so we're going to have to use two data structures. We're going to have to use a queue, and then we're going to use a set to actually see what to be able to constant time look up all the elements in the queue and check whether something's already in the queue. So let's go ahead and actually code this up. That was a lot of explanation, but let's write the code for this. So I'm going to create a class that's going to return an int, or a method that returns an int, and I'm going to call it delete. And it's going to take in a string query, and it's going to take in a hash set. That's going to be our dictionary. So that's going to be a hash set of strings, and I'm going to call it dictionary. So now we can first initialize our queue and our stack, or our set, sorry, that we're going to use to actually store our sort of loop when we do our breadth first search. And if you don't know what I'm talking about right now, you should go back and review just breadth first search as a general topic, because it's a pretty standard way of doing it. So hopefully this will make sense. But if you're confused, it's a good thing to know down cold when you actually go into your interview. So we're going to create a queue of strings. I'm just going to call queue. New. And we're going to create a set of strings that is going to be, it's basically going to mirror our queue in terms of the elements. And so we want to make sure that whenever we add or remove from the queue, we're adding or removing from the set, because otherwise if they get out of sync with each other, then it's going to get kind of weird. So I'm just going to call that queue elements. And then we're going to go ahead and add our query to our queue and our set, and that's going to kick us off. That's going to kick off our iteration. So we'll say queue.add query and queue elements.add query. So now what we need to do is we're going to create a while loop, and we're just going to iterate through as long as our queue is not empty. So we're just going to say while not queue is empty. And then we want to actually do something with our strings. So the first thing that we need to do is check whether our next string is actually in the dictionary or not. Because if it's in the dictionary, then we know that we're done. So we're going to go ahead and get the string from the queue. So string s equals queue dot remove. And remember what I said, we have to also remove it from the set so that they stay in sync with each other. So we're going to say queue elements dot remove, and we're going to remove s. And then we're going to say that if the dictionary contains the string, we're just going to return, we need to return the number of items that were removed. And so the easiest way for us to do this is we can just calculate the difference in length between our current string and the original query string. And that's obviously going to give us the number of characters that were removed from that string. So we can just do if dictionary dot contains s, then return query.length minus s.length, which is fine. And now, otherwise, what we want to do is we want to go through and remove each character in turn from the string and return, and then add the resultant string to our queue, so that we're going to make sure that we're basically going to imagine we're going through this. We're going to first try removing the A and add it to the queue, and then we're going to remove the B and add it to the queue, and then we're going to remove the C and add it to the queue, and that's going to basically allow us to go through the next level of our tree. So we're going to do for int I equals 0, I is less than s.length, and I plus plus. And then we're going to get the substring for that, where we remove that particular character. So we can do that by using the string substring method. And so we're going to create a string called sub, and that's going to be s.substring of 0 to I plus s.substring of I plus 1 to s.length. And as you can see, what we're doing here is substring takes the first element inclusive, or the first index inclusive, and the second index exclusive. And so we're basically taking the characters from 0 to I, not including I. So 0 to I minus 1, and then this is taking I plus 1 to s.length minus 1, or the end of the string. So what we're doing here is we're just chopping out the character that's at index I, and then we want to check whether this is in our queue already or not, right? Because that's going to allow us to prevent these duplicates. And so we're going to say if sub.length, well, actually, we're going to say if not queue elements dot contains sub, and also this is something that you might want to check with or that you would want to check with your interviewer, but you should confirm that a dictionary cannot contain empty strings. And the reason for that is that it's going to change how our code actually works. Because what I'm going to do now is I'm going to assume that we can't use, that the dictionary doesn't contain empty strings, and therefore I'm going to exclude any empty strings from our queue. So that way we know that when we get to the point where the string is equal to 1, the string length is equal to 1, and then we're trying to remove characters, we're not going to add the empty string to the queue, because that doesn't really make sense and that's not really necessary. But maybe you could have some weird language or dictionary where the empty string would be in the dictionary, and then that would also be interesting, because then you would never have a case where the you would always be able to remove some number and get a valid string, right? Because you could always just remove all the characters and end up with the empty string. So that would be an interesting twist on the problem, but I'm going to assume that we are not using the empty string in the dictionary ever. So I'm going to just also check that my substring length is greater than 0. And if it's not greater than 0, then I'm not going to add it to my queue. And otherwise, assuming that it is a legitimate string, I'm going to say that queue.add sub and queuelements.add sub. And then finally, the last thing we need to do is return our error in the error case, because this should return, as long as we find some valid value, this will return, right? But if it doesn't return and we get to the end, then we know that that's the error case. And in that case, we decided that we are going to return -1. So I'm just going to return -1, and then that is all there is to this code. So it's not a ton of code. It's a little bit tricky, but let's go through an example. Let's just go through this example that we have here. So we're going to say, let's say dictionary is this. And so we start with queue, which is going to be empty, and queue elements, which is also empty. And so we're going to first, and then our query is going to be ABC. So we start by adding our query to the queue and the queue elements. So we have ABC and ABC. And then we're going to come down, and the queue is not empty, so string S is going to be equal to queue.remove, which is ABC, and therefore we remove that from queue, and we also then remove it from queue elements. And we're going to check if this is in our dictionary, which it is not. So we come down here and we say, okay, so I is going to be equal to 0, and so we do, and then sub is equal to the substring from 0 to 0 plus the substring from 1 to 3. So the substring from 1 to 3 is BC, and we will check, and that's not in Q elements, so we add that to the Q. And then we also add it to Q elements. Then next, we are going to, I is now equal to 1, and we are going to take the substring from 0 to 1 plus the substring from 2 to 3. So 0 to 1 is A, and 2 to 3 is C, so we get AC, and then we're going to check that's not in Q elements, so we add AC, AC, and then we're going to go through one more time. So I is now equal to 2, and so we're going to take the substring from 0 to 2 and the substring from 3 to 3, which is AC, or AB, sorry. So we're going to add AB. And I'm sort of not going through all the details, but we're checking each time that that the string is greater than length 0 and that it's not in the subarray, or that it's not in the queue. And then we're going to come down to here and we're going to remove the next string. So we're going to remove BC. So S is now BC, and our I is equal to 0. And dictionary does not contain BC. So we're going to, and we also remove BC from the Q and the Q elements. And then we come down here. So I is equal to 0. Sub is equal to substring 0 to 0 plus 1 to 2. So we get the substring is B. And then the substring is C. And then we're going to also add that here. We go through, we increment I to 1, and now our substring is B. So we add that. And then we're going to iterate back through. Our new S is going to be AC, and we remove AC. We're going to try and add A, which is going to be fine. And then we're going to say that the substring is equal to C, but C is already in here, so we're not going to add it. So we loop back around again. We remove AB. We go through it again. Both A and B are in here, so we don't add them. We're going to remove C. We're going to remove B like this. We're going through quickly now, and we get to A. And now we're going to, so our S is equal to A, and now dictionary.contains A. So we're going to return query.length minus s.length, which is 3 minus 1, or 2, which is what we expect here. And finally, just to go through, let's imagine that our dictionary was this instead. So just to test the error case, we see that it's not in the dictionary, so we go through one more time. We're going to, so we've now removed this, and our queue is empty. So we come back to the queue is now empty, and then will break out and return -1. So that's all there is to this problem. Hopefully that made sense. The last thing we need to do is look at the time complexity, which is the sort of unfortunate part of this problem. But we can look at this in terms of how many times we're doing the operations, right? So the first time we're going to go through, you could also look at it in terms of this tree. So let's go back to the tree that we had at the beginning, which was ABC. And then there's 3 children of that, and I'm not gonna write everything out, but that has 3 children, then that has 2 children. And then each of these is 1 character. So what we get here is we get that the first level is n. So I'm just gonna start multiplying stuff together, and that's probably the easiest way to do this. So from our first level we get n substrings, or we get n possible combinations, and then on the next level each of those is going to have n minus 1. So here we have n minus 1, and then if we imagine a longer string, we would then, each of those subtrees would have n minus 2 children, and so on and so forth. until we get to 1. And so what we get here, because what we're doing is for each, so it's like when we start with our original string, and then our original string, we have a substring for every child. So for every possible character that we could remove, which is n substrings. And then for each of those substrings, we have n minus 1 more substrings. So we're just multiplying together to get some sense of what we're working with here. And then what we can do is we can just multiply this out. And I'm not actually gonna multiply this out, but what you get is, so this is like big O of this, and what you end up with is that this is equal to big O of n factorial. That is n factorial, right? Is n times n minus 1 all the way to 1. So that is not a good runtime. And we should mention, or I should mention at this point, that this is not actually going to be the runtime, right? Because we came up with these optimizations where like we did this here with the set where we're checking and we're removing duplicates. So remember that big O notation is just an upper bound, and this is an upper bound on the runtime, and for all intents and purposes, this is good enough for computing our runtime, but it is a little bit more, if you wanted to get more precise, you maybe could, but this is the gist of it. So hopefully that makes sense, and let me know if you have any questions on the YouTube comments below or on the blog, or tweet at me or whatever you want. And otherwise I will see you again next week with another problem.